basically. And class of chaperones, these chaperones have two subclasses, which is class 1, that are group 1, which is prokaryotic in origin, and the group 2, which is eukaryotic. So group 1 has a distinct co-chaperone ES, whereas the group 2 does not have co-chaperone ES. And there are substrate specificity for group 2, but the group 1 is promiscuous. So they are, these are important in protein folding. So Untitled showed that protein can fold by themselves in vitro condition for ribonuclease in 1960s. But later on, when Art and others found that this does not hold good inside the cell, they realized that the component like chaperones are necessary for protein to be folded in the cell, and this is because the cell is highly cluttered, and this is a cluttered atmosphere. It's like a jam-packed tube in Kolkata and a high peak time. So this is the reason why we need chaperones in the cell for rescuing the proteins that are basically prone for aggregation in the crowded atmosphere. And these are also necessary for, various Alzheimer's disease, prion disease, Huntington disease are all basically because of the non-native protein interaction and amyloid beta sheets forming non-native, hydrophobic interactions. And all these are implicated in protein folding. So that's the reason it's quite important to understand the mechanism how the non-native protein is recognized by GROEL or the chaperones. So this is a general functional cycle which has been described, which is being debated as well recently. So this is from 2001 Neil Ranson, where the non-native protein binds to the ATP region, and the ATP opens up the cis cage, and the co-chaperone comes and binds to the cis cage, and the protein folds within the 10 seconds of the half-life period of the cis chamber. So if the protein does not fold, or if it is folded, in either case, after the half-life period, the negative cooperativity allows the ATP to bind to the trans ring, and when the ATP binds to the trans ring, it triggers the cis chamber to release the substrate and the co-chaperone. And that's the cycle which is repeated again and again. If the protein is folded, then it has found its destination. If the protein is not folded, it is again captured and it on the trans ring, and then it becomes the cis ring for this cycle, right? So that's how these images show ATP bound form and ADP bound form, ATP bound form, ADP bound form. There was no information of ATP bound form with the substrate, and that's what we were aiming to do. With some initial disasters, we were able to look at it, but what we looked at it, we will see in few minutes. So these are the mechanisms of GROEL with the non-native protein, how they bind, and when did I start? 11:30, isn't it? 11:15? Okay. So another half an hour I have. Maybe I'll finish early. Okay. Okay. 12:15. Another half an hour. Good. So the basic mechanism of GROEL is basically, I can show you then. So this basically is the dynamics of GROEL. We call it as breathing. So when the ATP binds, the intermediate domain moves by 25 degrees and the apical domain moves by 60 degrees at about the axis in the apical domain and rises by 60 degrees. So it rotates by 90 degrees and rises by 60 degrees. So this movement basically turns the cis cage, which is basically hydrophobic earlier, which would used to look like yellow here, turns it into hydrophilic, and this hydrophilic region is conducive for protein folding. So there are debates like whether this protein is actively being folded by the GROEL or passively being folded. There are two groups which argue for the same thing. This hydrophilic chamber is now conducive for protein folding, and the non-native protein which is pushed into the chamber is capable of folding within this chamber. And this is free from the cluttering of the cell. So it basically, people call this cage as Unfinson cage or infinite dilution cage, because it is like infinite dilution within the cage, and it is free from the cellular cluttering. And this was an important aspect of chaperoning, basically. And this is how the ATP bound form basically changed its shapes and forms a co-chaperoning bound dome-like bullet shape, actually. These were all characterized by EM from the Helen's lab. So now our aim was not to look at the dynamics, but our aim was to look at a non-native protein bound to the GRO-EL, and in this case it was Rubisco for us. And Rubisco had been identified in the 1970s, but it had eluded the hands of earlier workers because it had some problems inherently, because it is a non-native protein, and whenever they do complex, they were unable to visualize it. So Wachu and other groups, they mutated some of the residues and they were able to visualize. Okay. In this case, what we did was we had a mutant version of GRO-EL, which we used for side orientation, but that GRO-EL was functionally active, and we wanted to trap that Rubisco using that mutant version. So we were aiming for visualizing a non-native protein, but a little bit of history about non-native protein. The first time a non-native protein was visualized is by Helen group in 1994, where they collected this GRO-EL non-native protein malate dehydrogenase complex. So you can see that 418 individual images. So with this, they were able to identify that the substrate was bound. And indeed, we know probably we'll be talking about how you can do a 3D reconstruction with minimal number of particles. We can discuss more because he is actively doing some research on that. So the porcine mitochondrial malate dehydrogenase was visible in the difference density map when they calculated, and this went to in 1994. It went to Nature, obviously. That was very important at that time. If we do this, we will not get even JMB this time. No. So I had to do something better. What am I doing, and what is so important? Because the Rubisco is one of the most important enzyme, because it brings the inorganic carbon dioxide into the Calvin cycle as an organic compound. So it is basically fixing carbon molecule, basically. And this process is amazingly slow. Most of the enzymes, when they have a turnover of 1,000 molecules per second or 2,000 molecules per second, this can have a turnover of as much as maximum 4 molecules of carbon dioxide per second. So the mechanism and activity is of large importance. So we initially tried to do a complex of GRO-EL with ES and the non-native protein, and that was the time when I moved there to Birkbeck, and Helen and Dan did a ternary complex of GRO-EL, ES, and with ADP and non-native protein complex. So we did. So that was my learning time. We did eigenimages. We didn't see any eigenimages as corresponding to density, but you see that there is some change in size. So this was done in automated data collection in scripts. So I don't know how automated data collections has to. Probably it's basically some user-centric focus because of that, or some non-monitoring in the data collection. This variation in size has happened, but what the main aim is that we were expecting some non-native protein density within the chamber which is folded, or within the trans chamber which is open. So we were not able to see. So the problem was more complicated. Actually, I removed the top image. Why it's there, I don't know. Okay. So then we wanted to simplify the ternary complex to binary complex. So we just went on to negative stain with GRO-EL and the Rubisco molecule, and then we tried to image it. When we tried to image it, we were not able to see any substrate molecule in the side views, because we were in order to do a 3D reconstruction, we have to choose the side views. So we chose all the side views, and that's exactly we were not able to see the particle. Why, we don't know at that time. But now we know why it was. So one of the reasons was that the non-native protein was non-specifically undergoing aggregation, and when we had a little bit of extra DTT in solution, so you see that this is the GrowEL and the non-native protein Rubisco. So it was in solution, so it was binding to the GrowEL. So then we were happy, and then we tried to do a negative stain again with this sample with 5 millimolar DTT. Again we were unable to see the non-native protein bound to the GrowEL. So we were puzzled, and we went ahead and checked the eigenimages of the end views. So if you think of a bottle, and bottle is pointing towards you, that is the end view of GrowEL. And the side view is the bottle which is lying down on the floor, basically. The floor is vertical in this case. So when we saw the end views, we could see some eigenimages which showed some information about the non-native protein. So we were pretty sure that the non-native proteins which were on the particle. So this is basically a typical orientation problem, which I said I will be discussing about. So in this case, all the substrate bound GrowEL were going into the end views. So this was a orientation problem. So we had to deal with that. So we just proved that the substrate is going to the end views by means of analyzing the eigenimages. When we did alignment with the aligned particle and subsequent reference, the eigenimages signal improves. So when you have eigenimages signal at a higher position, that is the vector 4 or 5 rather than 8 or 10, the signal is much higher for the substrate there. Okay. So then we were able to see occupied one and non-occupied one. So we used this eigenimage to separate into two classes, and then we were able to see the class sum. There was some density which was more in the center for the substrate bound one, and there was less density for the less substrate unbound ones. And that was pretty encouraging. And then we just wanted to verify biochemically that the substrate is indeed binding. So we increased the Rubisco concentration from lower to higher concentration, and then we were able to see that indeed the GrowEL concentration was increasing as we increased. But after a certain time, because the non-native protein concentration increases, it starts precipitating, and we had to do multiple rounds of Viva spin step, because you have to remove excess urea in the solution, because when we add non-native protein, it contains urea in it. So when we do the Viva steps, we used to lose protein, so that's why you don't see anything here. So then we decided that 1.5 micromolar was the best concentration for complex. And then we had a very small amount of D473 mutant, which is the elixir which I am talking about here. So we wanted that particular mutant version of GrowEL because it induces the side views. How, we will come to that. But before that, we had to prove by cryo that indeed the substrate was bound in the end views. So this is another example. Earlier we showed that in the negative stain it is having substrate in the end views. So now we are showing that in the cryo also the substrate is bound only in the end views. And then we basically took the mutant version of GrowEL. So what this mutant version is basically is, it is aspartic acid 473 mutated to cysteine, and this was conjugated with sulfur SMCC hexase tag linker basically. So this hexase tag was linked to this D473C mutant. So we had this cysteine mutant, and then this H tag was linked to it, and this basically is the dealing with orientation basically. So we now force the substrate bound GrowEL to go to the side views basically. So the idea is you have a carbon grid, you do the glow discharge, we do you have a carbon grid and you do a glow discharge in the air. So when you do glow discharge in the air, you get the carbon negatively charged, and the His tag binds to it, and it doesn't allow the molecule to go and stand up. So that was the way in which it was. We were able to do that. I'm not going into the details of this, but just to tell you that these were the reasons for why people were not able to see earlier the substrate Rubisco bound to the GrowEL. For example, one of the reasons was the buffer in which the complex was made had chloride ion, so we had to change it without chloride ion. Chloride ion induces some folding in the Rubisco. And later on we found that the aggregation concentration was pretty high. Critical aggregation constant, what we call, was pretty high than what we were using. So we had to reduce that below the critical aggregation constant so that it doesn't undergo aggregation but it binds to the GrowEL. And we had to avoid Viva spin because the non-native protein was binding and we were losing proteins. So we had to optimize that. And then finally the bull's eye was basically to use this to induce the side view basically, which I just now told you. And then these were crucial for visualizing the substrate basically. So we took a cryo, so this is an example of cryo image and negative stain image of the same mutant version with the substrate protein Rubisco. And we went ahead with the cryo image processing. These are the class sums and the eigen images. So these are characteristic views of the eigen images for tilts on the GrowEL particles. And as you go down, you will see that there is a density which basically shows that there is a substrate region in that. So these two eigen images were used to classify the number of particles into two classes basically. One was, in this case we did it as 3 because the GrowEL was, in one case it was down and another case it was up. So we wanted to classify into 3. One is unoccupied, one is top occupied and bottom occupied. So we were able to do that by using the eigen image classification, and that's how we got with. So in this case there is a substrate at the bottom, and in this case there is a substrate at the top, and in this case there is no substrate. So these are the 3 classes and the 3D reconstruction. So which I was talking analogous to crystallography. I was talking like it's like 3 crystal structures, or in this case it is 2 basically, because this and this is same. In this case, if you rotate this by 180 degrees, it's the same. So there is like one without the substrate and one with the substrate like. So then we were able to use that as a reference, and then we got 2 classes, occupied and unoccupied. And then the 3D reconstruction shows that the initial 3D reconstruction with 6,000 particles showed that by 2 if you do 3,000 APO without the substrate, and this is substrate bound GrowEL. So with that we were confident that we are seeing the substrate now, but we wanted to increase the resolutions. We wanted to improve the resolution by increasing the number of particles. So when we have limited number of particles, and if you want to increase the resolution, you can actually increase the number of particles, and you can actually go further to a certain extent in resolution better. And what is that limit? Steve may be able to tell me at the end of the talk. But so in order to improve the resolution and also improve the number of particles in each class sums, we went ahead to add up to 16,000 particles, and then we had to do a asymmetric reconstruction because the substrate bound one is asymmetric. It's no more D7 basically. So C7 basically. So we used the 15,000 particles and then classified into 3 different classes of 6,000, 5,000 and 4,000 particles. The substrate bound one was 2 classes. 5,000 had the best interconnecting substrate density, and APO one was the other one. So these are the end views of substrate bound region. So GrowEL with the substrate bound GrowEL with the substrate bound Rubisco basically in the binary complex. This is a movie which shows the 3D reconstruction from the class 1 classification and class 3. So this is, class 2 and class 3. Class 3 is APO. So this is what you see in APO. When you give higher weightage to the spatial frequencies, higher spatial frequency, you see helices separately. And this is the substrate bound class 2 basically. And we were able to finally see that. So one of the interesting thing about this is when the substrate bounds to the cis ring, the trans ring of this GROEL basically does not allow the substrate to bind. And this was not known why, but it was known that when substrate is binding to cis ring, trans ring doesn't bind Rubisco, whereas the other substrate which Helen's lab had worked, like malodehydrogenase and GP23, they were able to bind to both the ends. So we were able to see some variation in the trans ring, narrowing of trans ring when the substrate was bound to the cis ring, and that's what is shown in this slide. Similarly, the class 1 and class 2, we were able to see in both the substrate bound ones, there was some narrowing in the trans ring. And that is shown here actually with the cross section with class 2 and class 1 with the class 3. Class 3 is the APO one, which is in pink. And this is the 3D reconstruction of all the 3 classes. And then the substrate density that we are able to see out of 54 kilodalton is almost 20 kilodalton we are able to see there. So when we compare this Rubisco crystal structure with the non-native protein, we do not expect any secondary structure or tertiary structure to be associated with it, or the quaternary structure, isn't it? So one thing that came to very surprisingly to us was that when we compared this density with the density of class 2, so this is the class 2 density, and when we superpose the density, just by superposition, you see that there is a domain-like feature. So non-native protein do have some domain-like features from this 3D classification, class 2 reconstruction basically. And we further went ahead to do GROEL, ES, ATP in the cis ring and the ADP in the trans ring with the substrate with the substrate Rubisco. So this is a quinary complex, 5 components involved in it, and this was done using a mutant version of GROEL, because if you do not use the mutant version, the ATP will be hydrolyzed and it will go into a state where the Rubisco is folded and it will release from the chamber. So we wanted to look into symmetry is C1 symmetry. Asymmetric reconstruction was done with this. So we were able to visualize the non-native protein which was getting folded. It's like a child getting birth in the womb. It's like non-native protein. That's what I compare it always with. And we were able to see the density in the cis chamber. And the similar thing, first time when Dan did with the GP23, he was able to visualize the GP23 folded in the cis chamber. And this was the first time anybody had visualized a protein being folded in the cis chamber, and that went to Nature. And you can see that, as I said, there is a difference between the substrate binding feature. In this case, it binds to both the ends, GP23, but in our case, when Rubisco is binding to one end, it cannot bind to trans ring because it is narrowing in that region. And that was compared later on, and we were able to see that in the case of GP23 and malodehydrogenase, the cavity is indeed bigger compared to Rubisco-bound GROEL. This is another example. This was the first time we had a 3D reconstruction by Nada Villard in the Helen's lab. That was malodehydrogenase, and they were able to see that at least 3 consecutive apical domain was necessary for the protein to GROEL to bind the non-native protein. That was inference. With that, I will acknowledgements. Basically, Helen, who put up with me on Wellcome Trust fellowship, and Dan, who basically taught me Spider and image processing, and Art, who was our collaborator, who basically got Lasker Award for identifying chaperones, along with Ulrich Hartl in Max Planck Institute, Germany, and Elena, who was there always with me when I was there, and ISA TVM Directors, School of Biology faculties, who has been very helpful. The second part of the quinary complex was done after I moved here, so I went back to Birkbeck to do some data collection, and then came back and did the 3D reconstruction here. So I would like to thank Wellcome Trust for funding when I was in Helen's lab as a Welcome Fellow, and Department for my Ramalingasamy Fellowship, Department of Biotechnology, and ISA Trivandrum for all the support that I've been getting all these years. And we are having a big TEM room in the Biological Sciences block, which is being built. Probably when we go on 12th, we can go out a little bit and then see the floor before it is being built. So there is a CIF, which is being built with 2 TEMs, one 300 kV for material science and one 120 kV with all cryo facilities, which is probably, if we are lucky, would have been installed on the day when we go. The boxes which you saw on the entrance would be moved on 6th. Today is 5th, so probably it will be moved on tomorrow, I think. Hopefully, let us hope. Okay then. And I put something for Elena here. So that's Elena there at Bugbeck. Along with me, of course, I'm there here. Questions? No? GrowEL and Robisco has negative cooperativity. That's what I was showing, yes. So it doesn't matter whether it's trans or cis, because it binds to one end, it cannot bind to other end actually. So when it binds to one end, we call that as cis. Yes. Right. Soumya?
If we use a glow discharge, use either in air or in methanol, it makes the grids negative. But if we don't have access to a glow discharge, is there any other hack that we can use to make the grids negative charged?
Plasma cleaner is one way. You can just remove the top layer and it basically reduces the hydrophobicity of the surface.
But will it make it negatively charged then?
What charge? Yes, yes. If it is air, it will be negative, isn't it? And if
in
it
the
is
plasma cleaning?
Yes.
Okay.
In the plasma cleaner, yes.
So if
glow discharge is nothing but plasma actually. You apply a high voltage and it creates a plasma, and that plasma is what charges the surface.
Okay.
Yes.
Thank you.
You have plasma cleaner, I know that.
Yes, we have that.
Sir, you have done some mutation to stop the ATP hydrolysis in your study.
Yes, yes.
Why are you not using ATP non-hydrolyzable ATP analog?
That's also possible. So that was another alternative which we had. You can always use ATP analog as well. So there are structures which was done in the same lab earlier with ATP analogs and ATP ALF3. Basically, ALF3 is an analog of ATP basically. Yeah, we do all sorts of things. Whichever comes to your hand actually. It doesn't matter.
Thanks, Natish, for a nice talk. What was the final resolution for your structure?
So there was 11 angstrom for the C1 asymmetric reconstruction for the last one that you saw, quinary complex, and 8 to 9 angstrom for the binary complex.
Is it that your Ribusco was already folded and it could not be released? Is that the state you captured, you think?
It is not completely folded yet, but it has a reminiscent intermediate state which has 2 domains. So I would think that it captures the partially what you call, people call it as molten globule state. So that's what we are looking at.
Okay. Thanks.
Natish, you showed a video with GrowEL, an animation slide. Can you please go to that?
Okay. Tell me the question.
Is that obtained from the 3D map?
Yes.
From PDB or your own research?
It's from the 3D reconstruction.
Oh, okay. Is it fully docked into it, or I can see some of the residues at the back doesn't fit exactly?
Yeah, it's from the 3D reconstruction, so it's basically those regions do not have densities.
One.
Yeah. Yes.
Yeah,
those regions do not have densities, basically. From the 3D reconstruction that we did.
Yeah, I can see some of the residues over there.
Yes. It's true. If you reduce the contour, it will cover, that's it.
Okay. Thanks.
binds on the both sides, right?
Yes, yes.
Rubisco does on one
Doesn't
side.
on
So
side.
I'm asking that when Rubisco binds on one side, can MDH bind to the other side, or it cannot? Because in cells you have chaperone and you have multiple proteins all the time, right?
That's a good question actually. We have never thought of that actually. Maybe somebody else has thought of it, I don't know. But as long as the cavity which is there is bigger than the substrate molecule, it should bind. That's what I think. But if it is bigger than the cavity of the narrow cavity, then it may not bind. So because the chamber is like this, at the internal end only you have the hydrophobic patch, not at the exposure end. So if it is closed, it may not access that region, and if it is open, it may be able to access. If it is small, it may be able to reach there. Probably. Yes.
Sorry, I have a very short question. Actually, I want to show 3 models. One have the closing and the modification. I don't know. I think
yes.
So, yeah.
Three classes. So
classes, yeah.
2 with
so
occupied.
do you play with the threshold, or you just do the slashing? I mean intersection to show us. Just the picture show us. It's an intersection picture, or it's one is playing the threshold and.
It is basically the cross section of the 3 images. Cross section of the image.
Okay. Okay, that's it.
Of the 3D reconstruction, yes.
Okay, thank you.
It's just a cross section. You can do it in camera. Just show the particular section. So to show the region of cross section in that region. Mohit.
Hi, Dinesh. Thanks for this nice talk. I just want to know the number. I mean, you told us about the symmetric and asymmetric reconstruction. I'm just curious, like, can you tell me the difference of the number of particles? Like, how many number of particles were in the asymmetric reconstruction?
So around 6,000 particles were there in the asymmetric reconstruction.
Okay, and
6,000 to 5,000.
5,000 and 6,000.
Yes. In the symmetric reconstruction, when we did, we had total number of particles was 6,000 around, and then we extended to higher number of particles, and then we did the asymmetric reconstruction.
Okay, and the difference in the resolution was 8 and
8 to 9 in that, and here it is 11.
11. Okay, thank you.
Good. If there are any more questions, one more. Okay. If there are no more questions, we'll go and have lunch, and we will have the afternoon session. We will probably, what is the time now? 12:15. So we can leave at 1:15 sharp, so that we are there on time. Thank you.